Okay, in 5.6 now we're going to look at conditional probabilities. And I'd kind of used that word in the last section when I said these conditions. So it's these conditional just means that we are given a piece of the information. So each row in the contingency table is a conditional distribution given one event. So all the numbers associated with women here is a condition that we have selected a woman in our survey. So this is the condition. This is the event that it is a woman. So we're given that we selected a woman in our survey, and now we can ask questions about, given that we talked to a woman, what's the probability that she wants an MP3 or a camera or a bike? And the way we're going to write that is we're going to write the probability of the thing we're curious about given, and we use this vertical bar to stand for given, that we've selected a woman. So the way we would do that is we would find the number of women who wanted a bike, which is 30, and divide it by the total women, 251. And we would get about 12% of the people surveyed fit this category. They're people who want bike, and it's given that they're a woman. So to write this generally, we're going to write the probability of B, vertical line A, and again we pronounce that as it's the probability of event B given that event A has occurred. And this is called a conditional probability. Another way we can calculate it is, so we can calculate from the contingency table just by finding the rows and columns that our numbers match and dividing, or we can use this formula. So this is the probability of event B given event A is the probability that both of them are true. So, and we recall from last section that probability of A and B would be the row A in the contingency table with the column B, or vice versa. And so we find those two overlapping lines and we divide by the probability of A. Now it's important to, so the order actually doesn't matter on top. This could be B and A or A and B, but this does matter. So you always want to look here. The last letter here, or the last thing here, A, woman, whatever it is, has to be the same thing in the denominator. So we want to match these two things up to get the calculation correct. Now if we want, we can rearrange this equation. I can multiply by probability of A over here, and we'll get the probability of A and B, the probability that two events occurred, is just equal to the probability of A times the probability of B given A. And this leads to our, we talked about rules a while back in class, or last class I believe, and now we have the general multiplication rule. So the multiplication rule we showed in class was the probability of A and B is just probability of A times probability of B. We didn't have this part here, and that was because we assumed the events were independent. Well, this one does not assume that the events are independent. So this one is more general, and oftentimes it's more applicable. So the first one we showed you, probability of A and B is just equal to probability of A times probability of B. That's very specific, and you can only use it for given situations when we have independent events. This one is more general. Okay, so let's look at an example to really help understand this, because these can be tricky. So we look at what is the probability that a randomly selected customer wants a bike if the customer selected is a woman. So you're going to see stuff like that. It'll say if this or given this. So you want to see what's the given condition. So since it says that we have a woman, we're going to be looking in the woman row. But let's look how the formula works. So probability of bike given woman, we already calculated this before, but let's see how we would do it with the formula. So we would say the probability of A and B, so that's bike and woman, and again, so that number there would be the intersection of woman row and bike column, so we know it's 30, out of how many women, or actually out of, so 30 out of all the people, 478. That would be the probability of bike and woman. Then the denominator, so again, A and A, woman and woman, so we want to match those denominators. Whatever comes second should go in the denominator. So divided by probability of woman. Well, probability of woman is just how many women, 251. This is a marginal distribution, right? So probability of woman is the marginal total, 251 women out of 478 total people. So what you end up seeing is you get this probability, which is a joint probability, 30 over 478, and then we get a marginal probability, total women over 478. And if you notice, if I divide by 478, these actually cancel, and the probability is just 30 out of 251, and that is what we saw before, 30 out of 251. So we can get it this way from the table if we think about it, or we can use the formula, and the formula kind of helps guide us so we don't have to think too hard about it and make sure we get the right divisions. Now, what's interesting is if events A and B are independent, then the probability of B given A should just be the probability of B. So let me use an example for this. So I kind of used this in class, but I'll use it again. This would be like saying, what's the probability of rolling a 2 on a die given that it's raining outside? Well, this given here, I don't care if it's raining outside. It's not going to change the probability of my die roll. And so you can think of a bunch of these, right? So probability of drawing a jack of hearts given that it's 3 o'clock in the afternoon. I don't care what time it is when I'm drawing cards. Given that there's a weather condition outside, so there's lots of things that we could say, well, I don't care this part of the probability. So they're independent. But if we don't know, so this is the case where, well, I'm not sure if they're independent or not. I can't reason it out just with basic logic. So I have to look at this. So I have to calculate this, probability of B given A. Then I have to calculate the probability of B. If they're equal, then these two things are independent. A and B are independent. So the math will help guide us, is what we can do. So in fact, here's an example. So we ask, are prize, preference, and sex independent? So we're wondering if the probability of a bike, so we're wondering if the probability of a bike doesn't depend on women or men. So what we have to do is we have to calculate the probability of the person picking a bike given that they're a woman, which we already calculated at 12%. Then we look at just the probability of anyone picking a bike, so man or woman. So to do that, we look at the total. This is a marginal probability. Total bikes, 90, divided by total people, 478, and that's about 26%. So we compare these two numbers. We say, well, 12% is not equal to 26%, which indicates that it does matter if you're a man or woman in your preference for bike, so that these two things are not independent. There's a dependence there. If these were equal, so if it was 12%, 12%, then we'd say, okay, then it must not matter for gender. And oh, by the way, so it would also work if with this probability of bike given man would be 12%. It wouldn't not the gender would not matter. Now, this can get a little tricky because people want to then use this idea that with disjoint events we can just use the multiplication rule. So we can just multiply the two probabilities. So when we originally showed the multiplication rule, probability of A, where do we have that? When we originally showed this multiplication rule, we said A and B is equal to A times B. Well, now we're adding this twist. Well, people sometimes want to try that with disjoint events. They want to say, well, they have to be independent because they're not overlapping. So P A and B equals P A times PB. Well, let's think about that. So disjoint events are oftentimes, in fact, not independent. So let's think about a simple example. Let's think about heads and tails. If A is the event flip heads and B is the event flip tails, they're disjoint because they cannot overlap. One flip cannot give me part heads and part tails. So they're disjoint, but are they independent? Well, basically, the idea is if I flipped a head, then I know with certainty that I did not flip a tail. So there is kind of a dependence there in that knowing one precludes the other event. So we cannot just multiply the probabilities. In fact, here's some checks we can do for independent. Like I said, independence is sometimes hard to figure out in problems, so this will help us determine if our situation has independence. And we can just check again whether B given A is equal to B or A given B is equal to probability of A. And then we can check if A and B equals A times B. So on this one we'd have to know this probability, and we'd have to know the individual probabilities, and we'd have to calculate it and see if they match. For disjoint, we're going to check if A and B is 0. So if A and B is 0, that means there's no overlap. Or we can just decide if they can occur together. Like I said, heads and tails, we can never get head and tail at the same time. And that should do it for 5.6.